All right, hello everybody. So one more thing to say, a couple more things to say about epoxides, and then we'll move on to chapter 10. Last time we were mentioning that epoxides always open from the backside via SN2, but that when the two carbons of the epoxide are not identical, you have a choice as to whether you're going to attack carbon A or carbon B. And you have two different sets of conditions that lead to two sort of opposite outcomes in terms of what I have called regioselectivity, that meaning selectivity among different regioisomers, or in other words, constitutional isomers. So if you open the epoxide with a strong nucleophile under negatively charged conditions where OR minus is the leaving group, the reaction mechanism is SN2, but is dominated by sterics, meaning that the less sterically hindered carbon is the preferred carbon to open. In this case, it's the less substituted carbon B, and so you get the product where the OH ends up on the more substituted carbon of the original epoxide, whereas the nucleophile ends up on the less substituted carbon. And that's generally true when you're using a strong nucleophile under negative charge conditions where a negatively charged oxygen is your leaving group. However, you can also imagine opening the epoxide under acidic conditions where you protonate first, turning the epoxide oxygen into an even better leaving group, and then the nucleophile attacks. And what we observe here, based on the evidence, is the nucleophile attacks the more substituted carbon from the backside. And you get the product where chloro ends up on the more substituted carbon and OH ends up on the less substituted carbon. Note the difference between these two products. In both of them, the nucleophile in blue is going to be trans to the leaving group in green, right? The difference, though, is that the nucleophile in blue, when you open up the epoxide under acidic conditions, the nucleophile in blue ends up on the more substituted carbon. We talked about last time how this should be troubling to you because you have been told that there is no SN2 at a tertiary carbon. This is the one exception to that, though it is the exception that proves the rule. And one of the things I was saying is, just as class ended last time, is that the SN2 and SN1 mechanisms aren't as separate as we might like to think, but that rather there is a continuum of mechanisms that sort of spans that space between SN1 and SN2. What I meant by that is, if you think about in blue a pure SN2 mechanism, and what we're looking at is a reaction coordinate diagram where the x-axis represents the extent to which the nucleophile attacks, sort of from 0% to 100%, and then the extent to which the leaving group leaves, again from 0% to 100%. If we follow the orange pathway, the leaving group leaves first to give a carbocation, and then the nucleophile attacks, and that's the SN1 mechanism. If instead we follow the blue pathway, where the nucleophile attacks at about the same rate as the leaving group leaves, that's what we've defined as SN2. We haven't even drawn a pathway along the top where the nucleophile attacks first and then the leaving group leaves, because that would require a carbon with 5 things bonded to it, which is not a good intermediate. But you can see, as I mentioned last time, there's a lot of space in between nucleophile attacking and leaving group leaving that we can explore. And I proposed a purple pathway, sort of intermediate between the two, where the leaving group leaves to a large extent before the nucleophile keeps coming in. Now, remember that when the leaving group leaves all the way, you get a planar carbocation intermediate that may be attacked from either side equally. But it should follow then that if the leaving group has left mostly but not all the way, that there should still be some preference for the nucleophile to attack from the backside. Does that make sense? If the leaving group isn't gone all the way yet, it should be hard for the nucleophile to approach from the side where the leaving group's leaving. All right, so let's keep talking about that. And let's talk about what the characteristic of that transition state should be. If the leaving group is mostly 75% gone, what should happen to the carbon that it's left from? What should be on that carbon that the leaving group is leaving? A little bit of positive charge, right? Not a full positive charge. We would only see a full positive charge if the leaving group left all the way. But if the leaving group is 75% left, perhaps there's 75% of a positive charge. Now, let's go back and look at the two carbons. Of those two carbons, which one could bear a positive charge better? Carbon A or carbon B? A. Why? More substituted, and more substituted carbocations are more stable, right? Because of hyperconjugation. What's good for a full positive charge is also good for a partial positive charge. So what I'm saying is, if the leaving group leaves most of the way, it's going to be better for it to leave from the more substituted carbon, which can better tolerate the buildup of positive charge. So now some things are starting to come together. Let's draw what this transition state looks like. I'll draw it in purple since it's the purple pathway. We've said that in the transition state, the leaving group is going to leave mostly from the more substituted carbon. So this is more substituted carbon A and carbon B. The bond between carbon B is going to be between the oxygen and carbon B is still going to be a wedge. It's still going to be strong. Let's see now, as that leaving group is leaving, in the intermediate previous to that, we had a full positive charge on the oxygen. There should be less than that now because the oxygen is taking its electrons from carbon A and leaving. There should be a bigger positive charge building up on, and in fact, maybe we'll just erase that small positive charge and forget about it. Most of that positive charge should be felt on carbon A, although it's not a complete positive charge, and that is because the leaving group is not completely gone yet. And then we can draw the methyl group sort of pointing downward on carbon A. Though we can't draw this really perfectly well, you're going to have to sort of imagine as the leaving group is leaving and we're building up positive charge on carbon A ought to flatten out a little bit. It's not going to be perfectly planar. It's not going to be a full carbocation. That would be if we took the orange pathway. So it should be somewhere in between, carbon A should be somewhere in between sp3 hybridized tetrahedral and sp2 hybridized planar. That's going to be difficult to draw. I'm just going to sort of splay that methyl group out like this. But you're going to have to imagine that its geometry is not quite all the methyl groups puckered in one direction, all the alkyl groups puckered in one direction for, as would be the case for an sp2 hybridized carbon, an sp3 hybridized tetrahedral carbon, but rather that carbon's flattened out a little bit. And that's going to make space for the nucleophile to approach from the backside. And there's going to be a partial negative charge on the nucleophile, not a full negative charge because the bond formation has already begun. But if you sort of follow along our diagram, it would look like this bond here is around 75% gone, whereas this bond here is only maybe 25% made. That gives you a sense for what's going on in this transition state. So the regioselectivity of epoxide opening under acidic conditions is governed by the fact that you protonated the OH group, you made it a better leaving group, and it starts to leave. It leaves from partially leaves from the more substituted carbon, which can better tolerate the positive charge. Nevertheless, the nucleophile still attacks from the back because the leaving group isn't 100% gone yet. All right? Some people will call this, if we want to muddy the waters even more, some people will call this an SN1-like SN2 reaction because it involves buildup of partial positive charge on the more substituted carbon. Okay? We're going to see another reaction that follows a similar pattern like this in Chapter 10, and so what you learn from this is definitely applicable to some more places. All right, questions about that? Okay, practice that because you're going to need to know two different regiochemical outcomes for opening epoxides under negative charge conditions versus acidic conditions. Okay, so before we move on to Chapter 10, I want to say a little bit about epoxy resin. Anybody ever repaired a surfboard out there? No? Maybe somebody? Yeah, good. How about, so in my shower over the past couple weeks, I've noticed there's a little hole in the fiberglass. So I ordered some epoxy to fix it. It's going to go really well. I bet you won't even be able to tell that there's a hole there when I'm through with it. It's going to be very aesthetically pleasing. Fortunately, the only people that ever have to see it is us in my family, so you won't ever have to. Well, maybe I'll bring a picture. If you've ever done any repair with epoxy resin or glue, it always comes in two packages, which are fine, but you mix them together, and then you have to hurry up after you've mixed them together before the glue solidifies. So I'm going to show you just briefly what that glue is and how it works. It involves an epoxide, which is why it's called epoxy resin. So now you're learning that connection. Anytime I do this, people want to know, do I need to memorize this for the exam? And I don't like to ask questions that involve memorizing facts, but I also don't want to say, no, this isn't on the exam, because I know you, and I know despite your desire to learn, you also have priorities, and so if I tell you that it's not going to be on the exam, some of you are going to stop listening. So what can I say other than I will continue to do on exams what I did on the first exam, which is there'll be a few small low-stakes questions on applications that we've talked about. So it may be worth looking at your notes or reviewing the video. But certainly I'm not going to be, which of these is the memorized structure of the one epoxy molecule you showed the one time. Okay, so with that, pay attention. Be concerned, but not overly concerned. Keep your distance, Chewy, but don't look like you're trying to keep your distance. I don't know, fly casual. So some of you recognize that quote, others do not. It is fine. So you have when you go to make epoxy resin and use it as a glue, there are two components. One of them is an epoxide, and that's shown here. But it's not just any epoxide, it's called a bis epoxide because there are two epoxy groups, one on either side. And you have this somewhat rigid linker of benzene rings and a tertiary carbon between the two. This is an aside, doesn't matter, but some of you have heard of bisphenol A or BPA and seen plastics advertised as being BPA free. This is bisphenol A. It has some activity against estrogen receptors, and so that's one of the reasons why people don't like to have it be in plastics that are involved in food. In any case, the key is you've got an epoxide, and notice that the epoxide has two carbons, A and B. One is more substituted than the other. So there's going to be some regioselectivity in epoxide opening. That's held in one tube. In the other tube is the curing agent, which is the nucleophile. And the curing agent is a bis or diamine. It is an amine. It's a molecule that has an amine on one side and amine on the other side. These molecules, like the bis epoxide or the diamine, by the way, I don't really know when to use bis and di, so we're using both of them and hoping for the best. These are bifunctional molecules. That means they got reactive handles on two ends. And you can see that if that's the case, you can imagine having a nucleophile on one end of an amine attack the epoxide on one end of the bis epoxide, and then the two molecules that you've now linked together still have two reactive handles on either end, and so you can make polymers. Okay, so here's an example of what can happen. Here's here's the nucleophilic amine opening the epoxide on the less substituted carbon, because the amine is a strong nucleophile. And then you end up with this 1,2 substitution pattern. I'm not showing you. You got to remember that over here is that rigid benzene linker with an epoxide on the other side, whereas here is just one amine having reacted with one of the epoxides. That amine used to be a primary amine. Now it's a secondary amine, but it's still a nucleophile. And so it can react again to make another bond with another epoxy group on another bis epoxide molecule. So now you have one amine portion linked to two bisphenol A, two bis epoxides. Remember, each of these orange things on either end has another epoxy group that can react. But the amine now has another end with the primary amine on it that itself can react with two epoxides. So there's one, and there's the other. And pretty soon, with just one amine, one curing agent molecule, you have linked 4 bis epoxides, each of which has its own reactive handle. And we can do this again, and again, and again, and again, until we have a rigid network. And that's too orderly. It should be way more messed up than that. But a rigid network of what used to be epoxides linked together by curing agents. And that reaction happens fast, but not so fast that you mix them together and it's still a liquid that you can apply to whatever and stick things together. It works as a glue because it infiltrates surfaces and pores on surfaces, and then solidifies and then keeps stuff linked together pretty strongly. I'll let you know how it works as I try to apply it to that hole in the shower. It's worked some other, anyway, and results may vary, but hopefully we'll see. Anyway, that's epoxy resin. That's what's going on when you use a lot of different glues work this way. If it says epoxy on the product, this is what's going on inside. Okay, so with that, we're ready to move on to chapter 10. And we're going to contrast chapter 10 with what's happened in chapters 7 through 9. The real difference in chapter 10 is what the nucleophile is. In chapters 7 through 9, the nucleophile was basically a molecule with a high energy lone pair. So the HOMO of the nucleophile was a lone pair on something negatively charged or on something neutral. In chapter 10, the nucleophile is going to be a pi bond. And of course, the HOMO of the nucleophile is going to be an alkene. And of course, the HOMO of an alkene is the carbon-carbon pi bond. Now, this introduces an interesting challenge. When, for the SN2 chemistry in chapters 7 through 8, 7, 8, and 9, when the nucleophile attacked an empty orbital, it was really clear where you were forming the new bond. Let me just show you, let's see, I don't know, shall we use, I don't really know what's going on with the Apple Pencil today. It's kind of being funny. Maybe if I link it, okay, plenty of charge, let's try that again. Anyway, the nucleophile in, I'm trying to choose what should be the nucleophile and I can't decide. Let's just have it be CH3O minus. And then the leaving group was, say, alkyl chloride or something like that. It was really clear what we were doing because the lone pairs on the nucleophile would attack the sigma star. You break the bond with the leaving group, and you end up making a new bond between the atom that had the lone pair and the atom that had the leaving group. Excuse me. This is such an emotional topic. Sorry, I don't know what's going on. The difference when you use an alkene as a nucleophile is that the two electrons that are in that HOMO are shared between two atoms. So there's going to be a question as to which atom gets the new bond. Let me give you an example. Sorry. All right. So, and I'm choosing this example deliberately. It's a six-membered ring. We're going to put a methyl group on one of the two carbons. And then on the other carbon, I'm going to put deuterium. You may think that's a dumb choice. Why would I use deuterium instead of hydrogen? I'm doing it on purpose. Deuterium is an isotope of hydrogen. It has a proton and a neutron, so it's twice as heavy as hydrogen. We use it sometimes in organic chemistry when we want to have a hydrogen that's labeled so that we can tell where it came from. So for now, just let it be that way. And our electrophile here is going to be an acid HCl. All right? Now, let's predict, HOMO attacks LUMO. The alkene here is going to be your Lewis base or your nucleophile. Oh, man, I really do not like the way it's printing my handwriting today. I think I need to reset may need a new tip on the Apple Pencil, or I may need to reset the iPad. In any case, the nucleophile is the alkene, so we're going to be concerned as to what the highest occupied molecular orbital is, and it is the carbon-carbon pi bond. Let's draw that pi orbital on the alkene. You've seen pi orbitals before. There's a continuous lobe of electron density between carbons A and B, hovering over, so that carbon-carbon pi bond is in the plane of the page. There's a lobe of electron density above the plane of the page, and there's an identical lobe of electron density below the plane of the page. But it has opposite wave function sign, which is why I'm changing the color. All right? But you have to imagine that this pi bond is both above and below the plane of the page. So that means if it's going to act as a nucleophile, you have to worry about whether it attacks from its top face or its bottom face. Alkenes have two faces, a top face and a bottom face. And we're going to have to worry about whether attack happens from the top face or the bottom face. The second thing we're going to have to worry about is, as the nucleophile attacks the electrophile, we're going to have to worry about who gets the new bond. Now, the electrophile, the LUMO of this electrophile is the hydrogen chloride sigma star. We've done this before. You're going to attack on the hydrogen because Cl- is a great leaving group. So, to show this reaction happening, HOMO attacks LUMO, I draw an arrow from the alkene electrons to the hydrogen, and then we break the hydrogen-chlorine bond and the leaving group leaves. Now, some of the products from this point are easy to draw, others are not. The first, of course, is Cl-. Should be pretty easy to draw. That's a good leaving group, but that's the boring one. So now let's talk about what the structure of this molecule should be after we've added that hydrogen. Okay, so there's going to be two considerations, two things to worry about. Who gets the sigma bond to hydrogen, the new sigma bond to hydrogen, carbon A or B? And the second thing we have to worry about is whether the attack occurred from the top face or the bottom face. We'll answer the second question first, and the answer is you have to consider both. Just like in the SN1 reaction where we had to think about the nucleophile attacking the empty p orbital from above or below, with alkenes we're going to have to consider attack from the top face or the bottom face. So yeah, the answer to that is we have to consider both. We're going to see both products, attack from the top face or the bottom face. Now, who should get the new sigma bond to hydrogen, A or B? Well, let's think through this. If A gets the bond to hydrogen, what will happen to B? It's going to be a carbocation, right? Because you took those two electrons that used to be shared between A and B, you took them away from B, and you used them to make the new bond with hydrogen with A. So there's going to be a plus charge. Okay. Similarly, if B gets the hydrogen, A has the plus charge. So now you can see where we're going. We're going to talk about carbocation stability again. Which is the better option? Should the positive charge be on A or should it be on B? A. Why? Because more substituted carbocations are more stable because of hyperconjugation. So the question, who gets the new bond to hydrogen, A or B, leads us to something that is called the Markovnikov rule, which, you don't have to memorize the names of rules. You don't have to memorize rules that are named after dead people. You don't even have to memorize rules that are named after live people, but your text will use this, and I might occasionally use this. But the rule here is the plus charge goes to the more substituted carbon where it is more stable. And the sort of corollary to that is that when the nucleophile attacks something, when the pi bond attacks something as a nucleophile, the thing it attacks goes to the less substituted carbon so that the positive charge can be on the more substituted carbon. So with that in mind, let's draw the products that would come from this. I'm going to start with a product that would come if the nucleophile reacted from its top face. So that means that the new bond with hydrogen is going to be on atom B, and the hydrogen is going to be up because the orange lobe did the attacking, and so we made the new hydrogen bond, the new carbon-hydrogen bond on the top face of the original alkene. Because hydrogen is a wedge, deuterium has to be a dash. By the way, this is why I chose deuterium, so you could tell that the hydrogen was added from the top face. The other carbon should be planar sp2 hybridized carbocation. All right, but I said that we have to get, because the top face and the bottom face of the alkene are identical, we also have to observe the other product where hydrogen adds to the bottom face of the alkene such that hydrogen is a wedge and deuterium is a dash. By the way, if you follow along, we just made a stereocenter, and it follows that if your starting material is not chiral and you make a stereocenter in the product or an intermediate, you have to make both configurations of that stereocenter. And we get those by attack from the top face or the bottom face of the alkene. Yeah?
If the A carbon attacks the hydrogen, wouldn't it also be equally substituted like the deuterium?
No, that's a good question. If the A carbon were to get the hydrogen, I will just draw one of those possible intermediates. Would that be similarly substituted because of the deuterium? No, deuterium for all intents and purposes is exactly like hydrogen. It's just a little bit heavier. but deuterium can't, like hydrogen, can't engage in hyperconjugation. Hyperconjugation is where an adjacent CH bond can line up, oops, didn't mean to erase that, can line up with the empty p orbital here. If it's deuterium that's adjacent to the empty p orbital on the carbocation, there's no other CH bond here that can line up with it. All right, other questions? Yeah?
So the major product that we'll observe is the one according to the rule, and the one you just drew a pretend that we didn't. That's not, we're not gonna see that.
Right, we don't observe this. So you wouldn't need to draw that, and in fact, drawing that would be wrong, which is why I'm going to erase it. Okay, I will point out just as an aside, I'm showing dashes and wedges here to illustrate the stereochemical issues that are going on with this reaction. But if I wanted to communicate that I get both possible configurations of the stereocenter, I could simply use lines, and that would communicate the same thing. Okay? Yes? Let's see. It looks like if we attack from the top face of the nucleophile, then the one on the right is from the top, and then the one on I always get left and right wrong my first try. I'm really sorry about that. The one on the left is top face. The one on the right is attacked from the bottom face. I think it's genetic because my grandma and grandpa are still alive. They're 95 this year. But she says that she used to have to tell him to throw a rock to identify his right hand. Dale, throw a rock. Which hand do you... Okay, it's this one. All right, got it. I mean, I'm right-handed. I know which one's the right hand. I just call it the wrong thing. Go ahead.
Could the chlorine, after the reaction happens, act as a nucleophile and attack the empty p orbital?
Yes, excellent. So the question is, what happens now? Could the chlorine, which was our leaving group in the first step, now attack the empty p orbital? Yes. So, and actually you've seen this before. You didn't notice it at the time, but back when we were talking about HOMO and LUMO, we did an example like this. After you've made the bond with hydrogen, you have a new electrophile, which is the carbocation, and the LUMO is the empty p orbital on the positively charged carbon. And then you have a new nucleophile here, which is Cl-. So absolutely, the next thing that happens is the nucleophile is going to attack the positive charge. This part isn't a new reaction. This looks like the second step of an SN2 reaction. I'm going to draw the empty p orbital on that positively charged carbon. And you're going to remember that this empty p orbital is both above and below the plane of the page. Equal above and below the plane of the page, though with opposite wave function sign. And that's true both for the carbocation on the left and for the carbocation on the right. As we saw before in the SN2 reaction, in this next step, as chloride attacks, we're going to have to worry about does Cl- attack from above or below? And of course, as was the case for the SN1 reaction, the answer is both. So I'm now going to show Cl- as a nucleophile attacking the positively charged carbon. This can happen from above or below. And what's true for one is true for the other. Though I'm just going to draw that arrow. So what this means is I expect two products from the carbocation on the left and two products from the carbocation on the right. Let's show you both of those now. So from the carbocation on the left, Remember there, the hydrogen was a wedge and the deuterium was a dash. If chloro attacks from above, chloro should be a wedge and methyl group should be a dash. So this is the top above product, I guess we could call it. Then if top referring to the fact that hydrogen in the first step got added from the top face. If chloro attacks that empty p orbital from below, then we should get a product where chloro is a dash and methyl is a wedge. This is the top and below product. Okay. Now we will see exactly the same thing for the other two products. Both of these products come from the carbocation in which hydrogen was a dash and deuterium was a wedge. If chloro attacks, oops, that's an eraser. If chloro attacks from above, you would get, oops, this product. This is the bottom above product. And then I guess I need to slide things over because I'm out of space. And then if chloro attacked from below, you would get the product where chloro is a wedge, is a dash, and methyl is a wedge. Oops. Okay. And this would be the bottom below product. All right. So I'm just going to use color to highlight a couple of things. We'll use maybe blue for the hydrogen. Oops. And we'll point out where the hydrogen ended up. And then let's use green, if that's okay, for the chloro group, and we'll highlight where the green ended up. Okay. So we get 4 products. Let's look at the relationship between those products. And let's sort of describe these products. In the top above product, the hydrogen and the chlorine are both wedges. They are both end up on the same face of the original alkene. Here's the original alkene, and here you can see hydrogen and chlorine are both on the top face of that original alkene. Because they're on the same side, you could say the relationship between them is cis, but there's a term that organic chemists use that your text will use to describe this, and because your text uses it, I'll use it now. This is called syn, for like synonym, sameness. They're on the same side of the original alkene. In contrast, the top below product has the 2 groups that were added to the alkene on opposite sides of the original alkene. This is the anti-product. Similarly, the bottom above product is also an anti-product because the Cl and the H end up on opposite sides of the original alkene, whereas the bottom below product is also a syn product. Stereochemistry is coming up again. What is the stereochemical relationship between the top above product and the bottom below product? These two. A, enantiomers, B, diastereomers, C, not even stereoisomers, D, same compound. A, enantiomers, they are. How can you tell? They have opposite configuration at each and every stereocenter. Carbons A and B are now stereocenters, but they're not meso compounds, and therefore they are chiral and are enantiomers of each other. Similarly, you should be able to see that the relationship between the 2 anti-products is Those are also enantiomers. Now, how about the relationship between a syn product and an anti-product? Diastereomers, right? You can tell that's true because they have opposite configuration at one, but not both stereocenters. Similarly, this syn product and this anti-product are also diastereomers. And then I suppose there's one other relationship we could talk about. It's these two syn products are also diastereomers. The relationship between any syn product and any anti-product is diastereomer and has to be. So this relationship between, this is too many arrows. That's also diastereomers. Okay, so the point is that in this reaction, we do see what's called Markovnikov regioselectivity because the chloro group ends up on the more substituted carbon, but we do not see any stereoselectivity at all. We don't see any preference for one enantiomer over the other. We can't. And then second, there may be some preference, but you generally get a mixture of syn and anti-diastereomers. Now, why did I hedge on that? If you notice what I just said, I started to say there's no preference for one diastereomer over the other, and then midway through I hedged a little bit. The reason for that is diastereomers don't have the same chemical and physical properties. They don't have to form to the same extent or the same rate. So it is entirely possible that if you did this reaction, you might find some preference, 60-40, 70-30, for one diastereomer over the other. You absolutely cannot get a preference for one enantiomer over the other in this reaction. And so when you see a reaction of an alkene with an acid, HCl or HBr, I want you to draw both the syn and the anti-products, and I want you to draw both enantiomers of each syn or anti-product. Okay? This is going to be a multiple response question where there's going to be a lot of options. Here are the 4 that are correct. If you want to know what the incorrect distractor options are for this question, it's really easy. You just get this first step wrong. You put the hydrogen on the wrong carbon, and then you've got 4 other incorrect products to choose from. Yeah?
In this specific case, couldn't it kind of attack from the A carbon then to do a hydride shift?
Could it attack and make the bond with the A carbon first and then do a 1,2 hydride shift? Not thought about that. That's an interesting possibility. I don't know. There's probably ways to test for that, but I don't know. Good. Okay, so one quick thing which you're going to hate, I mean not really hate, but because I've said that all these 2 pairs of enantiomers, the syn set of enantiomers and the anti set of enantiomers, because these are all products of the reaction, it is possible for me to summarize these 4 products by drawing the following. Without dashes and wedges, I can just do that. And now you're saying, why the heck did you just waste 10 minutes, 15 minutes drawing all those structures when you could have just drawn that as a product? And I'm saying you have to know all the stereochemical possibilities before you can know that this is an okay answer. When I don't use dashes or wedges, I communicate that the products have both possible configurations at each stereocenter. 2 stereocenters, 2 configurations at each stereocenter, 4 products. Right? I saw a hand. Yes? Yeah. On the test, would you have all 4 of these plus that one? That would be me playing with your head, and I'm not going to do that. Yeah. So what I'm saying is this answer is okay when you're doing problems, and if you want to just draw that instead of drawing all 4. If that is, I could totally give you this as the answer for this question, and you could select that. I'm likely to do this just because I want you to pay attention to all of the stereochemical issues. But no, I'm not going to give you these 4 options and then this one and then have you wonder what on earth are you supposed to do. Yeah.
Would the carbocation intermediate, is there a product or
No, the carbocation intermediate is just that. It's an intermediate you don't isolate. The energy diagram for this reaction probably looks like this. As with the SN1 reaction, probably forming the carbocation is the rate determining step, and then nucleophilic attack in the second step is pretty fast. So probably it's a 2-step reaction like this with the carbocationic intermediate here. Okay, other questions? Yes? Why did I use the chlorine? I missed the last part. And the hydrogen? Okay, why did I highlight chlorine and hydrogen? I'm using that because it's the chlorine and the hydrogen that we are adding to the alkene. This is a new class of reactions called an addition reaction. It's not a substitution reaction because we're not replacing one thing for another. We're instead adding HCl to the alkene. And because of that, we're paying attention to H and Cl so we can tell where they end up. Did they end up on the same side of the alkene or on opposite sides? Yeah.
So it's not like other configurations where we care about the length or the size of these groups, it's just that they're in these groups.
Right, so it's not like absolute configuration. You could still go in and assign R and S here if you wanted to. Syn and anti are relative terms like cis and trans. You can use them interchangeably, but they describe the relationship between 2 groups. So yeah, syn product is the 2 things that got added are on the same side as the original double bond. Yeah. Sterically, does it matter that the 2 groups are on the same side or opposite sides? You can think of all kinds of reasons why you might expect the syn versus the anti to be different in stability. We haven't considered that yet, but there may be differences in stability between the 2. There may be preferences for one over the other. We're not going to get into that. We're just going to anticipate that all of them would be products. Yeah. Others? So this reaction has a name in your text. It's called, you're going to love this, hydrohalogenation of alkenes. It's called hydrohalogenation because you are adding both hydrogen and a halide to the alkene. Now, the second reaction in chapter 10 is like unto it. In fact, I'm going to get you started and then turn you loose over the next couple of days to mull it over. Same starting material, same issue here. You're going to use an acid. In this case, it's H3O plus. You're going to get a carbocationic intermediate. And then in your second step, instead of Cl minus, water's going to be your nucleophile. Everywhere above where there was a Cl, there will be an OH group. Okay? But it's exactly the same reaction. So it's best if you don't see what I just started drawing for you as a separate reaction, but rather as a variation on the same theme. Alkene attacks the acid, the hydrogen adds from the top face or the bottom face. You make the carbocation that's more stable, and then the nucleophile attacks. So before next time, I want you to draw the products. There should be 4 of them, and I want you to get the regioselectivity, the Markovnikov rule right. And we'll regroup on Friday.